This is an intuition for the convolution operation that I find helpful, so I thought I'd share it. Let's consider three wizards. At the same instant, they all generate a wave of water. At some locations, these waves overlap, and so the total water, the water in the room or the background, is higher in some locations than if a single wizard had generated just one wave. The answer to how much water is at any given location is what you get from the operation of the convolution, where this function w represents the wave that each of these wizards creates, and the function f represents the wizards themselves. So it's some function which is 1 where you have a wizard and 0 where you don't. You could also modify it so that the heights were different depending on the height of the wave each wizard generated, but for demonstrating the idea, we'll just go with 1 and 0. So now let's figure out what the formula is for this convolution operation. Let's consider this point here, which has been marked by the blue arrow. We'll label this point x. What is the contribution to the water at x from the wizard at this point y on the left? Well, we'll look up how much water a wizard wave has at a distance x minus y from a wizard. So that's the contribution there. So that's the amount of water coming from the left wave. And we'll multiply that by his wizard function, which is to say a 1 because there is a wizard. This just means that if we take a point that has no wizard, we won't add anything to the total water. And now we want to know the contribution from every wizard. And so we'll take a sum over all of the y's. And so this will take into account all of the wizards on the screen. This is equivalent to doing an integral with respect to y. And in fact, this is exactly our formula for the convolution of f and w. So this is our answer to how much water is at any point x, given that each of these wizards generates a wave w. So what's the utility? What can you do with this concept of a convolution? This is a metal rod. The wizards now represent hot spots on the rod, where their temperature is given by the size of the wizard. It turns out that this situation is very analogous to this wizards and waves example we've been talking about. Let's describe the initial distribution of temperature on the rod by a function f of x. It turns out that for a point of a hot spot on the rod will evolve according to this formula. It's not important to understand exactly where this formula comes from, only that it looks something like this. So we start out and instantly have some bell curve temperature distribution, and this diffuses across the rod over time. And the same thing is happening for these other hotspots. In fact, the temperature at any point is the superposition of the temperatures that would come from each of these hotspots. And so the temperature at any point x and time t is exactly this convolution which we've been talking about.